Hello everybody and welcome to the Pipeline Industry Guild webinar. We'll be starting shortly. The time's now coming up to 12 o'clock, so we'll look to kick on. Hopefully everybody's on the call that wanted to be on today, but this will be going onto the Pipeline Industry Guild YouTube page on completion, so hopefully people can revisit this event today at a later time. Big thank you to Neil from the ROSEN group today, presenting on the pipeline DNA and pipe grade determination. ROSEN and Neil won the Pipeline Industry Guild Land-Based Technology Award in our previous earlier this year, sorry. Huge thank you to Neil and the team here for presenting today. As you can see, we have a number of webinars coming up on a monthly basis now. Through November, December and February, and a number of other events also occurring in the real world rather than this digital world as we all engage. If I could ask people just to mute their own microphones if they're not engaging, that would be appreciated, and if there are any questions, if we could just capture them in the comments section as we go through, and then we'll reflect on those questions at the end of the presentation. So without further ado, Neil, I'm going to pass over to yourself and let you crack on with your presentation today as we go through the webinar. Thank you.
Okay, thank you, Dan. Today I'm going to talk to you about pipeline DNA and pipe grade determination. This is a new technology that the ROSEN group have been developing. It has been rolled out to a couple of years, or about 5 or 6 years ago now. They started being developed, and it's now in the full commercialization stage, and we've run approximately 50 projects across the world. I'm going to go through a couple of format of the presentation, talk about why it's needed and the challenge that we have, then talk a little bit about the technology that the ROSEN group, particularly our colleagues in Germany, have developed, talk about the benefit that we can get out of the technology, not only in terms of the pure data, but how you change that data into information and how you actually use it to help manage pipelines. A little bit more about the service and the product, and then give you some live case studies of what we've done. The challenge, this is UK specific, that the pipeline infrastructure is aging. Well, it isn't UK specific, it is worldwide. We have, as a company, inspected pipelines which are over 70 years old, and some which are even older than that. Ever since then, there have been decades of rerouting, there have been repairs, there have been ownership transfers, there have been extensions, which means that in any given pipeline, you can have multiple different populations. These will have been manufactured at different times, they'll have been installed at different times. Each different population may have come from a different pipeline or pipe mill, or different original feedstock. They all have different material property characteristics. They can all have different integrity threats. But you need a single integrity management strategy for the entire pipeline, and trying to develop this and making sure that it captures all of the populations can be challenging. The data that you use to manage the pipelines and inform the integrity management strategy is normally based on historic records and personal knowledge. These historic records were normally originally paper-based. They've sometimes been shifted from place to place to place with relocations or ownership changes. There may have been floods, there may have been fires, and sometimes, often, they are incomplete. If you want to verify your existing operating pressure, if you want to do an operating change in your operating pressure, any form of integrity management relies on accurate knowledge of your pipeline material properties. And without that accurate knowledge, any changes can be difficult to support. So how do we get around this? How do we square the circle that you haven't got the records, you don't know the properties, but you still need to be able to identify them? ROSEN recently introduced an inline inspection-based service, the Pipe Grade Sensor, to support this. It is based on proprietary eddy current technology with pre-magnetization of the pipe wall, and there'll be 2 site calibrations after this. The outputs of this service are strength values for each individual pipe and bend. You get established populations of pipes and bends with shared characteristics from it. With each population, we can then assign a grade, and that grade can then inform a structured and focused verification process beyond ILI. So just to re-emphasize what we're doing here, we are measuring the strength of the pipe. We are telling the grade of the pipe on a non-destructive inline inspection basis. So we're running a pick through and we're telling you what grade that pipe is. How do we do this? We've got some very clever technology that our colleagues in Germany have been developing. We have PGS sensors, the pipe grade sensors. They can be put on the same carrier as our standard MFL, our magnetic flux leakage pigs. So we don't need a separate inline inspection run, and we don't need to change the tool configuration. We can also use the information from the MFL run and the PGS run to offer a combined diagnostic solution. The PGS response will depend on the pipeline material microstructure. That can cover a multitude of different factors. It includes the microstructural phases present, so your perlites, your ferrites, your metastable phases, bayonites, martensites, etc. It does depend on the grain size. It depends on the lat space or the lamellar spacing within the perlite. It depends on multiple other factors, including dislocation density, amount of segregation, your non-metallic inclusions, etc., etc. Within our development, then ROSEN has developed proprietary algorithms which relate the sensor reading to the actual strength of the pipe. These are fairly complicated and they do need a lot of inputs and calculations, but it gives us an estimation of the yield strength and the ultimate tensile strength from which we can derive the appropriate pipe grade. The accuracy that we can get from this is plus or minus 6 KSI at an 80% confidence level following the calibration digs. So we can tell you what grade it is to plus or minus 6 KSI with an 80% confidence. Oh, sorry, Dan, can you just go back to the previous slide? I managed to skip over one. So this is what the pure technology can give you. This is the data. This graph is what comes out. On the left-hand side, you have the estimated pipe yield strength, and on the x-axis, you have the log distance. Each of those points represents a single joint. So the points there are the average yield stress for that individual joint. So you can see this particular pipeline is approximately 200,000 feet long. And apologies for the units, but we've done quite a bit of work in the US, so we have to work in feet and KSI as well as normal units. And you can see there that this average yield strength of the pipe is somewhere between 55 and 60 KSI. So that is what, about 400 MPa. Each of those points identifies an individual joint, and you can see there is a broad consistency down the length, but there are also some outliers. There are some areas of apparently higher yield strength, and there are some areas of apparently lower yield strength. That data there is useful as it stands because you can point out any obvious outliers. You can use it to verify or to support records that are available. It is useful as it stands. You get full value and full bang for your buck out of it. If you integrate it with other sources, you do the analysis and use it to inform your integrity management strategy. The first step to doing this is to split it out into populations. These populations are defined as groups of pipes with shared characteristics. So characteristics that we'll normally pick on as the major ones are the strength, the wall thickness, the diameter, the nominal joint length, and the pipe type. So pipe type as defined in the weld type. Was it seamless? Was it longitudinally welded? These characteristics tend to be unique to a particular pipe melt and construction campaign. And following calibration, we can assign each joint to a final population. So the graph above is the same as the previous one, but we have gone through the population process and we have split up that original lot of pipes into individual populations. Each color code on the graph or each color code and marker type identifies a different population. I'm not sure if you can see on the legend on the right hand side, but in this particular line we have identified 22 separate populations. So 22 individual combinations of original pipe mill, original grade, original wall thickness, etc., etc. This allows you to have a much better informed integrity management strategy, rather than just assuming that all of your pipe is, for example, X52 of 8 millimeters wall thickness. You can go through it and you can work out exactly which different grades it is, where the different wall thicknesses are, where the different pipe mills are. You can then use that to target your integrity management strategy. Within the different populations, we can also go through and we can assign the pipeline grades. The way that we do this is we'll know that if you get a single population from the same feedstock by the same manufacturer using a consistent process, then the distribution of strength from that population will be a normal distribution. That distribution is reflected in the PGS data, so we can then characterize each population accurately and we can reliably identify any outliers. If there's a large enough population, we can also assign the grade with a fair degree of confidence using the -3 standard deviations basis. This can mean that not only can we actually identify the grade, we can also look and we can identify the possible minimum strength that you get from that population. Often you'll find that the actual yield strength is significantly higher than the SMYS. So on the bottom graph on the right hand side there, you can see some distributions with the minimum yield strength for X42, X46 and X52 there, and the population in there. That population could be X42 or X56 or X46. The actual average yield strength of it would meet X52, but there will be a significant number of pipes below the minimum yield strength of X52. So we would call that probably X46 on the basis that it meets X46 comfortably. We can then clarify and we can confirm that grade assignment by the in-ditch work, the verification and the calibration. And types of work that we can do there include non-destructive strength determination, chemical analysis, we can do in-situ metallography, we can do wall thickness, do identification of the seam type, and we can do whatever else is possible while a hole in the ground is open, while we have access to the pipe. Other things that we can do with the information. We can help identify any risk that's present. Here we have got a similar graph, but we compare the measured yield strength against the records. So the solid red and black lines are what the operator's records stated that their SMYS was. You can see that in most cases, the measured yield strength is above the operator's assumed SMYS. You can also see there are areas of black lines which have a SMYS of 24 KSI. Again, this was an American line, and the regulations there determine that if you don't know the grade of a pipeline, you have to assume a yield strength of 24 KSI. One of the benefits of this service is that it has shown that even where they didn't have records, then the population appears to be very similar to areas where they do have records. You can see in most cases, the measured PGS yield strength is above what the operator thought they had. There are a small section at around about 16,000, 17,000 feet where there were a couple of pipes which were below the reported SMYS. This allows the operator to be able to better target their digs, better able to target their verification, and target their integrity management strategy. If the strength of the pipe was a major concern for them, then obviously they need to look at the lower strength parts of the line first. Other things that we can pick up from here is a different line, and you can see that the vast majority of that is a very consistent, very tight distribution, just under 55 KSI yield strength. In this particular case, then there are some areas which are lower strength. The two different areas that we have here of potential concern, the lowest strength pipes that we've measured, you can see are at about 200,000 feet. And they are somewhere under 45 KSI yield strength as measured. When you take that PGS measured yield strength and you integrate it with the other information, we will be able to tell, or we were able to tell, that not only was that lower strength, it was also higher wall thickness. Therefore, it's probably, well, it isn't as great an integrity threat, because although the actual yield stress is going to be lower, because the wall thickness is higher, the low bearing capacity is probably going to be equivalent. However, there is another area at about 170,000 feet log distance where you have both lowest strength and lowest wall thickness. That is going to be that area of highest risk for a pipeline operator, and where they need to do their concentration and look in terms of their verification strategy. So you can target it to, or you can target your strategy, you can target your efforts to accurately target where the potential issues are. You get fewer digs and you get more useful information than if you're just digging at random or assuming that the entire length of the pipe was from the same population and was consistent. The other thing that you can tell from this kind of data, those black points there were where the crack management tool that we also ran as part of this inspection identified potential crack-like anomalies. This is a good example of where you can get specific integrity threats associated with specific populations. So you can see these crack-like anomalies are associated exclusively with the blue population at the start of the line. That means that the operator will then know where to concentrate his efforts in terms of crack inspection and where to look for these anomalies. It enables better targeting, better interpretation, better evaluation of all the other inspection data. You can tailor your integrity management strategy to address the actual threats faced by each population. This slide is more written around the US market, but there is a big push there to define and validate the maximum allowable operating pressure of a pipeline. The general flow chart is on the right there, and it is well established. It tends to be both conservative in one way and also potentially unconservative in others. The assessments are often based on material strength data, which is currently either assumed or based on very limited data if you haven't run the PGS tool. As a result of this, you need large safety factors, and if your records are completely inaccurate or your assumptions are completely wrong, it can potentially still be unconservative. The pipeline DNA approach and the ROSEN PGS tool does allow the approach in the spreadsheet there to be challenged and to be improved. We can better target, we can better analyze, we can get a better picture of the strength of your pipeline and the integrity threats associated. A complete and a verified data set can both eliminate unnecessary conservatism, but it can also identify and highlight new risks which haven't been previously identified or accounted for. So to try and summarize where we are, the pipeline DNA, the PGS service, it is unique. There is nobody else who can measure the yield strength of a pipe on an ILI basis. It's groundbreaking. It allows complete ILI-based characterization of the entire pipeline using the PGS data, but also using all the other data. So the other ILI data that you have, any records, any geographic features. This data can be input into a holistic, coherent integrity management strategy. The real benefit that you get out of PGS is not only in the data itself, it's in the information and the management tools that you can get out of it. It is a currently live technology. We've either completed or in progress with approximately 50 projects. They are worldwide. So we have done continental Europe, we've tested in Argentina, we've tested in the States, gone through Mexico. We've currently got the first couple of runs in the UK, and we are in process of evaluating those at the moment. It is a genuinely new and innovative process, and I'd like to thank all my colleagues in ROSEN for permission to present this, especially my colleagues in Lingen, who were the ones who actually developed this and rolled it out. And most importantly, I'd like to thank the Pipeline Industry Guilds for permission to present this and the prize that we did manage to win with it, and also thank them for the opportunity to present on this webinar. So back over to you, Dan.
Thank you, Neil. Thank you, Neil. I'm just going to jump out of here and just see if there are any questions that have been raised from the wider community, or if anybody has any questions that's on the line, then please feel free to speak up now. It doesn't look like anything's been captured in the comments section. So if there are any questions. No? Okay, so thank you, Neil, for today. Again, just so everybody's aware, there are a number of other webinars coming up in the diary, but there are also a number of other events occurring around the Pipeline Industry Guild. If you visit the Pipeline Industry Guild website, pipeguild.com, you'll be able to see a number of events which are coming up over the coming months, including some other technical events, social gatherings, and keynote speaker events occurring. So once again, thank you very much indeed, Neil and ROSEN, for presenting today, and all the very best going forward.
Okay, thank you, Dan, and thank you everybody for dialing in.